have discussed the examples of isentropic flows and normal shocks, and we will try to utilize this understanding that we have till now to develop a feel of compressible flows through nozzles. So, we will first start with example of a converging nozzle. We have seen earlier that one of the important objectives that you have with a nozzle is to accelerate the flow, and to do that let us say that you have a tank, you connect a converging nozzle with the tank. We have seen earlier that the nozzle shape always need not be convergent, and in fact one could have accelerating flow with a diverging section also. So, that is a non-intuitive manifestation of the compressible flow, which is not there in an incompressible flow, because density variation also is very important. It is not just A into V is constant, rho into A into V is a constant, and rho variation is important. Now, let us say that this is connected to a chamber this is the reservoir where you have roughly the stagnation conditions prevailing. Here you have the nozzle, the converging nozzle. This is known as a plenum chamber, in which you have air maintained at the desired exit condition. The desired exit condition is not your choice, but the desired pressure that is there in the chamber that you may control, and there may be a discontinuity between the exit pressure and the pressure that you are having in the plenum chamber. The pressure that you are having in the plenum chamber is known as the back pressure. So, you have here the pressure as Pb, which is known as the back pressure. How you control the pressure here is by regulating the flow through a valve which is located in this pipeline. So, if you want to reduce the pressure, you may create vacuum by allowing more and more air from these to escape. So, what happens in this kind of a situation? Let us try to draw a graph of pressure. Maybe we draw the graph according to the nozzle inlet and the exit. So, we draw a graph of pressure versus x. We will also try to draw a graph of mass flow rate versus the pressure, the back pressure. We are plotting m dot by m dot max. M dot max is the maximum mass flow rate. So, we are normalizing the mass flow rate as a function of the Pb by P0. So, we are varying the back pressure. So, this is an experiment. Initially the pressures at the two places are the same. Now, we are creating lower and lower pressure by allowing the air to escape from this pipeline, so that the back pressure falls. So, when the back pressure falls, what will happen? So, let us say that the back pressure you have initially the back pressure falls such that it comes to a level like this. So, this is a pressure variation with x. So, when you have a low back pressure, what will happen? That because of this pressure drop there will be an added mass flow rate. So, initially there is it is quite intuitive, you have initially equal pressure, no mass flow rate. Now, you have a driving pressure gradient. So, you have a lower pressure here, you have a higher pressure here, that will drive a mass flow rate. What do you expect? You expect that as you reduce the back pressure you will have higher and higher mass flow rate. So if you make a plot like this, so if you reduce the back pressure you will see that the mass flow rate is increasing. In this way, so you reduce the back pressure, you have the mass flow rate increasing and increasing till you come to a very important limit, say this is the limit where the back pressure is equal to P star. What is the start condition? The start condition is the sonic condition. So at the sonic condition you will have Mach number equal to 1. See, you started with what Mach number? You started with 0 Mach number, so to say. So there was no flow initially, then your Mach number was increasing. In this way you are coming to a state where the Mach number is 1 and there you have a flow rate which is corresponding to a velocity which is same as the sonic velocity. Now if you reduce the back pressure further, so if you make a plot like this you will interestingly see that when you have a situation where Pb is equal to P star, you have P star by P0, then m dot equal to m dot max. So this will become equal to 1 and then if you reduce the pressure further mass flow rate does not increase anymore. So intuitive portion, intuitive variation of the graph could be something like this, that is as you reduce the back pressure there will be more and more mass flow rate, but this is not correct and you come to a saturation state which corresponds to Mach number equal to 1, beyond which further reduction of back pressure will not increase the mass flow rate. Physically why it happens? So remember that when you reduce the back pressure what happens? It is a pressure perturbation. This pressure perturbation travels within the fluid medium at a speed of the sonic speed relative to the fluid medium, it travels with the sonic velocity. So if you write say velocity of the disturbance relative to the fluid is equal to velocity of the disturbance minus the velocity of the fluid. What is the velocity of the disturbance relative to the fluid? It is in terms of magnitude it is the sonic speed. In terms of the direction, what is the direction in which the disturbance is moving? So disturbance is created in the downstream in terms of the back pressure, it has to propagate and go to the reservoir. Just in very simple terms, if you have to explain it to a say senior school student, it is something like this. So you reduce the back pressure, when you reduce this pressure this reservoir should know that yes the pressure is reduced, so I have to compensate it by increasing the mass flow rate. So as if here there is a decision maker who is sitting, who will know the message that there is a reduction in back pressure and accordingly will increase the mass flow rate. So the message has to propagate. What makes the message propagate? The speed at which the disturbance propagates is governed by the sonic speed, and because of the propagation of the disturbance in terms of a wave through the medium, that is how this reservoir knows that yes I now have to increase the mass flow rate to compensate for the reduction in pressure. So velocity of the disturbance relative to the fluid, if you just take the algebraic sign of it, it is minus c, because let us say positive x direction is right towards the right, so negative x direction is towards the left, equal to velocity of the disturbance minus when the sonic condition is achieved P star, then velocity of flow is c and velocity of flow is towards the right with a velocity c, and this shows that you have velocity of the disturbance equal to 0. What it means is that if you reduce the back pressure further, the message that such a disturbance is there is unable to propagate to the reservoir and make it actuated by allowing more mass flow rate. So, it is sort of said to be coming to a saturated condition for the mass flow rate, and in that case the technical name is that the nozzle is choked. So, the nozzle is choked, that means it has come to a critical mass flow rate beyond which if you reduce the back pressure further you will not be able to increase the mass flow rate, and the corresponding Mach number at that condition is 1. If you reduce the back pressure further, what will happen? Of course, you may be able to reduce the back pressure further, because reduction of pressure is your task, that is an exercise that you are experimentally doing. So, what it will do is if you reduce the pressure further, there will be a sort of oblique expansion wave outside, and such that at the end, so there will be something which is occurring in outside. We will not go into the details that what is occurring outside, but there will be some phenomenon that is occurring just outside, but important thing that we are getting out of this is that if you reduce the back pressure further, at least in terms of getting the mass flow rate, it will not improve any further, and you can find out what is that critical mass flow rate. What is the critical mass flow rate? M dot max is equal to rho star A star U star, right. What is A star? A star is the area of the exit in the converging nozzle. What is rho star? Rho star you can write P star by R T star, and U star is U is Mach number into C. So, M into square root of gamma R T. The start condition means Mach number equal to 1. So, U star is square root of gamma R T star. So, this is P star square root of gamma by R into 1 by square root of T star, right. You know the expression of P by P0, yes, into A star. You know the expression of P by P0, you know the expression of T by T0 as a function of Mach number. For example, T by T0 is 1 plus gamma minus 1 by 2 m square. P by P0 is T by T0 to the power, oh sorry, this is T0 by T, it is the other way. So, this is T0 by T, this is P0 by P is T0 by T to the power of gamma by gamma minus 1. So, you can calculate T0 by T star by substituting m equal to 1, and it will be a sole function of gamma. So, the expression here m dot max will be a function of what? P0, T0, gamma and A star, right. So, whatever is the maximum flow rate that you will get is decided interestingly not by the pressure, the back pressure which is there, but the pressure at the inlet section or the pressure in the reservoir, because these are the stagnation pressures and the stagnation temperature. So, this is about the converging nozzle. Let us consider what happens for a converging diverging nozzle. We can see that what is the limitation of the converging nozzle. if you want to accelerate a flow say from a subsonic state to a supersonic state, that you cannot get in a converging nozzle, because the maximum Mach number that you can get is 1, and that is at the exit below a critical back pressure. So once you have that, and still if you have an intention of accelerating your flow further, you also have to add a diverging section, and that is why the importance of a converging diverging nozzle. Before going into that, maybe let us work out a problem on the converging nozzle itself. So the problem statement is like this: air in a large tank at 100 degrees centigrade and 150 kilopascal of pressure exhaust to atmosphere through a converging nozzle with 5 centimeter square as throat area. Throat area means the exit area for the converging nozzle. Compute the exit mass flow rate if the atmospheric pressure is, number 1, the atmospheric pressure is like the back pressure, is equal to 100 kilopascal. So here there is no plenum chamber, it is exiting to atmosphere directly. So one is 100 kilopascal, number 2 is 60 kilopascal, number 3 is 30 kilopascal. Okay. So clearly this corresponds to the stagnation temperature, this corresponds to the stagnation pressure. So this, when these pressures are given, what is your first decision making? What is the critical back pressure to get the sonic condition at the throat? Okay. So that is the star condition. So we know that P0 by P is equal to 1 plus gamma minus 1 by 2 m square to the power gamma by gamma minus 1. So when you want the start condition, when you want this P star, then this is m star or this is equal to 1. So from here you can find out what is P star. So P star for this case is 79 kilopascal. Okay. So 79 kilopascal is your P star and your given pressure is 100 kilopascal. So for the one it is some state like this one, say as an example, which is greater than P star. So you have not yet come up with the maximum mass flow rate. So how do you decide that what is your m dot? That will be dictated by the rho a and u, which are in turn dictated by the Mach number. So what is the Mach number? So now you have P0 by P is equal to 1 plus gamma minus 1 by 2 m square to the power of gamma by gamma minus 1. What is for case 1, what is the value of P? 100 kilopascal. So from here you can find out what is the Mach number at the exit. So when you know the Mach number, basically all the expressions are derived in such a way you know all the flow parameters. So m dot is equal to rho exit into a exit into u exit. So rho exit is P exit by RT exit into A exit into U exit is Mach number exit into square root of gamma RT exit, right. And T exit by T also you can T0 by T using the expression of T0 by T is 1 plus gamma minus 1 by 2 m square. From that you can find out what is T exit if you use m exit. T0 is given 293 273 plus 100 373 Kelvin. So from here once you get T exit you may substitute all the values to get m dot, and this m dot is going to be 0.15 kg per second. Now consider the cases 2 and 3. When you consider the case 2, you see that your decision making now says that the pressure is less than the critical pressure, that is P star. That means the saturation in the mass flow rate has already been achieved, and therefore for calculating the mass flow rate you should not go through this route, but you should go through the m dot max route. So for both 2 and 3 you have m dot equal to m dot max, this is rho star A star into U star which we have just derived. So these you can write exclusively in terms of the stagnation properties, in terms of P0 and T0, and A star is the area of the exit or the throat area, throat is the exit for the converging nozzle. So if you calculate this will come out to be 0.157 kg per second. So you can see that this is greater than the previous mass flow rate, and this is the maximum mass flow rate that you can get from this nozzle. So with this background now we will go to the converging diverging nozzle.